Hello, class. Okay, so we're going to talk about the connection between electric potential and electric fields. And so what we're going to do is we're going to show that, well, there is a connection between them, and specifically what that means is, say you know the electric field. We can find the potential in that region as well. And similarly, if we know what the potential looks like in a region, we can find the electric field in that region as well. So like given one, you can always find the other. And I have to emphasize that we are talking about electrostatics here. So we have charges that are fixed, not moving around. That can complicate things. But for now, our charges are all fixed. We're talking about electrostatics. And yeah, it's remarkable that this connection exists, where if you know one, you know the other. Because say like the electric field in an area, like say this board. Say we know the electric field everywhere. If I pick a point on the board, we have this electric field. Well, on this board, this electric field contains two pieces of information at this single point. More generally in space, an electric field contains three pieces of information. It has three components. Where if I know the potential at this point, I know one piece of information. Just what the potential is. It's a scalar. And so the fact that you can go back and forth between them. If you know the potential, you know the electric field. That's kind of remarkable that this this scalar function contains the same information as a vector function. And the reason why is that in electrostatics, the kind of vector functions that you can get from static charge distributions are special. I can't go into more detail about that unless you've taken Calc 3 and learned about vector calculus. But that's not a prerequisite, so I can't go into any more detail than that. I'll just mention electrostatics, the curl of the electric field is 0, and that kind of leads to this result, but I won't say any more on that. Okay, so we're going to start out, say we have an electric field in some region. So we have these electric field lines that just totally random. Say they look like this. And I want to know what the potential looks like in this region. So let's consider this charge, Q, moving from, say, point A to point B. So let's look at the little, we're going to, of course, we want to calculate the work. And so we're going to break this up into pieces and integrate from our starting point to our ending point. So let's just look at one of these pieces. This one's convenient because we have this electric field line crossing through. And again, that's just the drawing. There's an electric field everywhere, so the electric field exists at every point. But the drawing shows one there. So in order to find the work just over this segment ds, we'd have dw would be F dot ds, or Q E dot ds. And so if we integrate over the entire path, we have work is equal to Q times the integral of E dot ds. Going from A to B. Now remember, work is equal to minus change in potential energy. And so we have minus delta U is equal to Q integral E dot ds. And now let's divide by Q. I'm going to put the minus sign over on the other side as well. So we have delta U over Q is equal to minus integral E dot ds. And this right here, so we have our basic result, delta U is equal to Q delta V. So delta U over Q is delta V, and well, this is an important result, so I'm going to write it on the other board and keep it there. This is delta V, this is VB minus VA. So VB minus VA so that is so if we have the electric field, we can find the potential difference between any 2 points by integrating that electric field over any path connecting those 2 points. Because it's a conservative field, so you can pick any convenient path. And so we're halfway done here. We've got, given the electric field, we can find the potential. And before we go on to the next step, given the potential, let's use that to find the electric field. I want to go back and talk about there's a consequence of what we just drew here, we just showed here. So I want to go back and look at this idea of an equipotential region. So let's say we have an equipotential line. Again, a region, it could be one-dimensional, two-dimensional, or three-dimensional. Let's just say it's a line to make things easier. And let's say the electric field crosses, like in this region, looks like this. And let's call this point A. Let's call that B. It doesn't even have to line up really with the electric field. But, yeah. Okay, so let's look at this result that we just derived. Let's say VB minus VA. So we're going to integrate the electric field over this line segment, minus sign, and then we integrate E dot ds from A to B. And so let's call this like the x direction here. So like we can break our vector up into an x and y component. And E dot ds well, really, ds is just dx. It's we could just do that, but either way. Okay, so just applying what we showed just a few minutes ago, VB minus VA is minus the integral EX dx from A to B. However, VB minus VA is 0. Because both points A and B are on this equipotential. And so what this means is that EX equals 0. Now, we have to be a little careful in jumping to this conclusion, because it's not necessarily true that if an integral equals 0, then the integrand has to equal 0. There's examples that are easy to see. Like say you have f of x equals x, and you integrate from say minus 1 to 1, that's 0, but this function is not equal to 0. However, we can, these points A and B, they can be anything. So, like any points along this equipotential. And so the only way that this integral is always going to be equal to 0 is if Ex is equal to 0. And so what we've proven here is that the electric field has to be perpendicular to an equipotential. It cannot have any component along the equipotential. If there is a component along the equipotential, that means that the potential is changing, and we can't have that just by the definition of an equipotential. So that's a very important result. One example we'll talk about later of an equipotential is a conductor. Kind of mentioned this earlier, that in a static case, inside a conductor, the electric field is 0. So if you have a region where the electric field is 0, then this integral is 0, and like if points A and B are any points inside the conductor, then VB minus VA is 0. Those 2 points are at the same potential. And so a conductor is generally an equipotential, unless you have like a changing electric field. But we're dealing with electrostatics now. And so, yeah, it's like a practical example of a potential. And so if you have, say, like a metal plate and you charge it, the electric field has to be perpendicular to that plate. You can't have an angle there because the conductor is an equipotential. Okay, so we found how to find the potential given the electric field. Now let's go the other way. Let's say we have the potential and we want to find the electric field. So you're going to draw some potential lines. And we're going to consider a small region of space. And so again, these are equipotentials. And we know the electric field is perpendicular to that. So like the electric field at this point would look like this. It has to be perpendicular to this equipotential. And let's consider some displacement. Like say we have, ds can be anything. So there's an angle between these two vectors. And if we go through this small displacement ds, actually I want to, let me think about this picture for a second. I want to make a displacement across an entire, label these v plus dx, like the spacing between each is a small voltage change. Sorry, this should be dv, not dx. That made no sense. So we're talking about a very small change in potential, like the spacing between each of these equipotential lines. And I want to make this displacement completely go from one line to another. Yeah, give me a second just to think about there's another result. Let's look at, let's say we have a positive charge. We know V is kq over r, and if it's a positive charge, we're going to get positive numbers. So an equipotential around a positive charge, it might look like this. It'd be like a spherical shell around a charge. We're just drawing a cross section, so it's a circle. And let's say this is 100 volts. Then if we go to a larger radius, R is bigger, so the potential is smaller. And so we have this positive, and if we draw the electric field, use a different color for that. We can see that our electric field is going from high potentials to low potentials. Now, what if we replace this with a negative charge? So a few things happen here. One is our electric field line reverses direction. So that's our electric field. And the signs, of course, are different because Q is different. So if we put Q as negative, then we get negative values, but numerically they would be the same. And so in this case, minus 50 is bigger than minus 100. We're not talking about magnitudes here. We're talking about its actual values. And so again, electric field is going from high potential to low potential. So I want to draw this picture accurately. I've got to get the electric field in the right direction, first off. So it should go from high to low. So our electric field would actually look like this, pointing in this direction. And let's consider a displacement. Let's see, which way do I want the displacement to go? Let's say our displacement looks... And again, I drew it like it's a fairly large displacement. Again, we're looking at tiny changes in potential. This is a small displacement. And so now, this picture looks a little better. We're going from electric fields going from high potential to low potential. That is the correct way for it to go. And we have some arbitrary displacement. And so generally there's going to be an angle between the displacement and the electric field. So let's consider the work done over this small displacement. Let's call it dW. And again, that's going to be the integral of, not an integral, it's an infinitesimal displacement. So that's just going to be F dot ds, which is QE dot ds. Or we could write this as Q E ds cosine theta. Now let's look at this equation here. Delta U is Q delta V. So if we look at the change in potential energy, that would just be Q dV. Sorry, dV. Let's call this du as well. Again, tiny change in energy because it's a tiny displacement, small change in voltage. And we're going like from here to here. So we have the final value V plus dV minus V. So the change in energy is Q dV. And the work is minus the change in potential energy. So we have dW is minus Q dV. So here, let's put these two together. We have dW is QE ds cosine theta. Its dW is also minus Q dV. So let's put these two together. So we have Q E ds cosine of theta is minus Q dV. And the Q's cancel out. And we can write this as E cosine theta equals minus dV ds. So the Q's cancel out. Now, if there's no mathematicians around, you can say we divide by ds. I know they don't like it when you say that. But the result is good. This is just the differential form of this. Different ways of saying the same thing. Okay. Now, what is this E cosine theta? This is the component of the electric field in the direction S. So again, we can break this vector E into components. Yeah, like it's a little weird because we'll have like a component. Yeah, we could break it up into components this way. So like this is our S component. And this one is perpendicular to that. Let's not even give that a name. But we can see that ES is E cosine theta. So again, it's probably easier to see if, say that, like this is your S direction. So like if that's your electric field, if we have a small angle, then this would be E cosine theta. However, for this angle is 180 minus theta, and that just gives you a minus sign. Like the cosine of 180 minus theta is just cosine of theta. And so, yeah, like even in this case, they're in opposite directions, that's fine. So ES is E cosine theta. And so what we have is ES is minus dV over ds. So we consider the displacement in the direction ds. And we see that the S component of that electric field is the rate of change of potential in the direction of the displacement. Now, in Cartesian coordinates, we can write it this way. You know, we can always break our vector up in multiple ways. In Cartesian coordinates, we can say that EX is minus dV dx. And EY is minus dV dy. And EZ is minus dV dz. So again, if you know the potential in a region, you know the electric field everywhere in that region. You can get it just from taking derivatives. And this is extremely useful because we talked about finding the finding the electric field using Coulomb's law, basically, where you just integrate. You have an element of charge, dq, like the electric field due to a point charge, the magnitude anyways, is kq over r squared. And for a continuous charge distribution, you consider a little piece of that charge distribution. That's your element dq. And that gives you the electric field at a point, and then you integrate over the entire region where charge exists. And that's complicated in part because you're dealing with a vector. That this is just the magnitude, but the electric field due to that charge has a direction as well. And so like when you add up all the charges, you get all these vectors pointing in different directions. That complicates things considerably. And so when you look at the problem of finding the electric field due to a charge distribution, one strategy is just use the definition of an electric field and integrate. But now we have another way we can do that. We know the potential due to a point charge, just KEQ over R. Or we could say, dV equals KE dQ over R. So we can consider a charge element dQ, find the potential at some point we're interested in, and then integrate over the charge. And that gives us, well, when we integrate, we get the potential in that region. And this is a much easier thing to do most of the time. So again, for a given charge distribution, finding the electric field working with vectors, much more complicated than just integrating a scalar, like potential. And if we find this scalar function, then we can take derivatives and get the components of the electric field. And usually taking derivatives is not that complicated. And so it's kind of like breaking up a problem into two pieces, but the second piece is kind of trivial. So usually this is a better way to find the electric field if you want to, by finding the potential first. So this is a very important relation. Again, both ways. If you have the electric field, you can use that to find the potential. If you have the potential, you can find the electric field. And so a great connection between these two concepts. If you know one, you know the other. Now, I have an example, but I can do that in a separate video. So, yeah, I think that's going to be it for this one. Let's see, yeah, nothing, yeah, so that'll be it for this video.